We are now going to talk about OSPF metrics, OSPF database, and the different LSA types. So in this module we are going to cover what are the different link metrics, how are these values constructed, how they can be modified, and then we are going to look into what's in the OSPF database, what is contained in the database, how this information is kept in the database, how we can look into this information, and finally we are going to spend some time looking at the link state advertisements or the OSPF data units that carry the information about the routes and our topology, and we are going to explore them in some detail. OSPF metric is called cost. The reason why it's called cost is really just a traditional historical reason, because OSPF cost, OSPF metric, is automatically or can be automatically calculated based on the bandwidth. And the assumption there is that the bandwidth costs some money. So when the OSPF was designed, the cost was chosen as the name of the metric to kind of reflect this sort of monetary cost. It really has nothing to do with the monetary cost. As I said, OSPF cost is automatically calculated, is automatically determined based on the bandwidth. And there is a number in OSPF, a certain bandwidth, which is by default 100 megabits per second, which is called the reference bandwidth. The reference bandwidth simply means that this bandwidth will have cost of 1. This was fine when OSPF was originally designed, and remember, RFC was written back in, I believe, 1998. But these days, when we are talking about the multi-gigabit links, we are talking about the gigabit links, we are talking about the 10 gigabit link, 40 gigabit link, 100 gigabit links, using 100 megabits per second as the reference bandwidth does have some very interesting side effects. The side effect for that is that even if we had an interface that has 1 gigabit per second bandwidth, or let's say 10 gigabits per second, these would still be perceived by OSPF as having cost 1 by default. Now, this behavior can be changed in OSPF implementation in iOS using the global command in the router OSPF process called autocost reference bandwidth, and then specifying the value, which is actually in megabits per second. So the default value here is autocost reference bandwidth 100, but in this case here I'm specifying that the autocost reference bandwidth would be 10 gigabits per second, which seems like a reasonable thing to do these days. You might actually want to consider using higher reference bandwidth as well. Smaller bandwidth, smaller links with less bandwidth, they're going to have their cost proportionally increased depending on what bandwidth they have. For example, by default, the 10 megabit per second link will have the cost of 10, and 1 megabit per second would have cost 100, and so on and so on. This is if we leave the cost calculations to OSPF and to the routers to determine themselves. However, the cost for individual interfaces in iOS can also be configured. And this can be configured using two methods, an indirect way and a direct manipulation of the cost. In both cases, this has to be done on per interface basis. An indirect calculation of OSPF cost is setting the logical bandwidth on the interface. So for example, setting bandwidth to 1544 is going to set this to 1.5 megabits per second, which is the default bandwidth perceived by, for example, serial interfaces in OSPF, in iOS. And this would result in having a calculated cost of 64. But we can also directly set the OSPF cost, again on the interface, if we use the command IPOSPF cost 64. So how is then cost calculated in OSPF? Well, it's calculated using Dijkstra algorithm, the SPF calculation. But going through the SPF calculation every time when you need to determine a cost between two nodes in your network may prove to be a little bit counterproductive if you want to do it manually. So the best way to do it is basically take a look at your network, and let's say that you have a certain path that you want to calculate. So let's say that we have routers 1, 2, 3, and 4, and behind router 1 we have some network N. What we would look here, it would be the cost on the interfaces that are facing in the direction where our traffic would follow. So for example, if we wanted to send the traffic in this direction here, we would look at the outgoing interfaces on all of these routers, and we would look at what is going to be the cost on these interfaces. So let's say that the cost here was 1, that cost here was 10, that the cost here was 20, and let's say that the cost here was 1. So if we wanted to calculate what is going to be the cost from router 4 to N, here we are simply going to add these up. So we are going to have 1 plus 10, that's 11, plus 20, that's 31, plus 1, that's 32. So we are going to have the cost of 32 for this path. So this is a very, very simple way to calculate what is going to be the cost, if you know which path your traffic will take. So you can see from this very, very quick overview how OSPF metric, OSPF cost in comparison to, say, EIGRP metrics and EIGRP metric calculations is much, much simpler. And that's true. OSPF is complex in certain aspects, but when it comes to the cost, when it comes to calculating what is the actual metric, that's a very simple thing. But there is one thing that I forgot to mention. When you are specifying the cost on a particular interface here, there is a maximum cost that you can specify. A single interface in OSPF cannot have a cost that is higher than 65,535. Let's now take a look at some of the very, very basic cost manipulations in iOS. I have already explained them here, but let's see them in action. To do that, I'm going to continue with the example that I used before. I'm just going to use my R1 and R2 routers here, and they are interconnected on gigabit interfaces 1, and the network between them is 192.168.12.0/24, and I already have OSPF configured between them. But one thing that I have done in the meantime, I have added a loopback interface on R1 with the IP address 192.168.01/32, and I have also added this into my OSPF. So on both ends here I have OSPF process number 1 running, and I have OSPF in area 0 running between them. So let's take a look at what we have here. If I go to R1, if I run show IP OSPF interfaces brief, which is a very, very useful command to run in OSPF to kind of quickly get an overview of all the configured interfaces, I'm going to see here that I have 2 interfaces enabled for OSPF in process ID 1, and both of these interfaces are in area 0. I can see the IP address configuration on them, and here I can see what is the configured cost on these interfaces here. And I can see that both of my interfaces here have a perceived or calculated cost of 1. And if I take a look at my show interface gigabit 1, I'm going to see here that the bandwidth, the logically configured bandwidth here is indeed 1 gigabit per second. But if I take a look at my loopback interface in this version of iOS, this is the value that I'm going to be seeing here. And this is, if I'm not much mistaken, 8 gigabits per second. Now, with this value here, or is it 8 gigabits or 1 gigabit? Yes, it's 8 gigabits per second. So for whatever reason, OSPF shows me this as the cost. Not OSPF, but this is what iOS is showing me as the bandwidth there. But if I take a look at the interfaces as they are perceived by OSPF, both of these interfaces, even though they have the same bandwidth, they are showing up with the same cost. The reason for that is that the default value of the reference bandwidth in iOS is 100 megabits per second. So let's change this and let's set it to be 10 gigabits per second, for example. So I'm going to go to R1 and I'm going to say router OSPF 1, and I'm going to say auto cost reference bandwidth, and I'm going to specify the bandwidth in terms of megabits per second. So what I'm looking here is 10 gigabits per second. So I'm going to set the value to 10,000 megabits per second. And when I do this, I'm going to get this warning message that tells me to ensure that the reference bandwidth is consistent across all routers. Now, in my case, it is not consistent. On R2, I have not done this, but there is really not going to be too much harm done in my case of two routers connected with a single interface. But if you are doing this in a production environment, this could lead to some very undesired results. So make sure that if you are changing the reference bandwidth, that you actually do change it everywhere in your network. So with this change, let's see how this has impacted how my interfaces are perceived by OSPF. If I do show IP OSPF interfaces brief, now what I'm going to see here is that the costs, these are before the change and these are now after the change. I'm going to see that interfaces have indeed changed the way they are perceived. I can see that loopback 1, which is very, very close to 10 gigabits per second configured. It's configured as 8 gigabits per second, but there is not enough granularity to actually include this as cost 2. It is still going to be perceived with cost 1, but my gigabit interface is going to be perceived now with cost 10. So this now does show the difference between the 10 gig interface and the gigabit interface. Let's fix the same thing on R2 just to be consistent here. So I'm going to go to router OSPF1 and I'm going to say auto cost reference bandwidth and I'm going to set it to 10,000. The next thing that I would like to show you here is let's go ahead and change manually the cost on our loopback interface to not be 1. Let's change it to be, let's say, 2. So if I go to my interface loopback 0 here, I can do this using two methods. One would be to actually set the bandwidth here to be 5 gigabits per second. And if I'm not much mistaken, this is, oh, well, I'm not anywhere close there. So let me see. Oh, maybe I just need to wait a little bit. No, let's try to change it to lower it to, let's say, 3. How about if I set it to 1? Well, that doesn't seem to do the trick. Perhaps the loopback interface in this version of iOS always will have cost of 1, maybe not calculated based on bandwidth. Now, this comes as a surprise because it usually is calculated based on bandwidth. But you see, you learn something new even when you are recording videos to train someone else. So let's change this cost. So I'm just going to say IP OSPF cost here, and I'm going to set it to be 2. This will work. So if I do show IP OSPF interfaces brief, now I can see that my cost was indeed changed. So mental note, in this version of iOS, which is 15 something very, very high, the bandwidth, the OSPF cost for loopback interface is not determined based on the bandwidth. As I said, totally new thing for me. Now that I have cost of 2, and on R2, if I take a look at my interfaces here, I see that my gigabit interface has cost of 10. So if I go back to my whiteboard here, so now I have on this loop back here, there is cost of 2, and this interface here has cost of 10. So if I wanted to send the traffic down this path towards this loopback, what would be the cost that this traffic, or of the path that this traffic would have to traverse? Well, I'm looking at 2 here and I'm looking at 10 here, so I'm concluding that the cost must be 12. So if I go to R2 and if I do show IP route OSPF, when I take a look at my route for 192.168.0.1, I can see that indeed cost was calculated as 12. So I can see now, even in iOS, I have the confirmation of what I explained before, how the costs are calculated throughout the network. Now, thing to keep in mind with this is that what I have shown you here is not necessarily how routers calculate this cost. They would go through the whole implementation of the SPF best path selection, of the calculating the tree, calculating the graph, adding the candidates route, removing them, adding to the stack, removing from the stack, but I'm not going to bother you with that, because this is the best approach to actually do it with your own eyes and not go through the manual calculation of the SPF. Unless you are a computer science major and you are studying for your bachelor degree in computer science, you really don't need to know how to manually compute your SPF trees. Let's now talk about the OSPF database. OSPF database in iOS is a single source of information where the data about the routes learned and exchanged and injected in OSPF by the local router are kept. These routes, or this information about the routes and the links in our database, is kept and organized using the link state advertisements, or LSAs. So the LSAs are data units that are kept in the database. But the database is not flat. That means that there is no single OSPF database. These LSAs are actually organized into logical units, into logical entities. And there are multiple databases that exist in OSPF. If you are running OSPF with no external routes in a single area, let's say area 0, in that case we are indeed talking about the single database. But if we have multiple areas in our network, we are actually going to have multiple databases. And the routers that are sitting between these areas, the area border routers, they are going to have multiple databases as well. So let's say that we had a router R1 that sits between area 0 on one side and area 1 on the other side. Router R1 will have the database in area 0 and will have the database in area 1. Now, a fundamental concept in OSPF is the database integrity or the database synchronization. The databases within the area on all the routers, so those databases that are shared in that particular area, they must be identical. There must be no differences anywhere in that database. If this is not true, if there are some discrepancies in the database, first of all, by design in OSPF, we shouldn't see any discrepancies. But if we encounter them, we know we are dealing with some problem, with some bug, that is something that you cannot solve yourself. But if that was permitted, that could lead to terrible, terrible loops in our network. So OSPF requires two components to create a loop-free environment. One component are synchronized databases. That means that every single router in the area is using the exact same information to calculate the paths, and then it requires a loop-free calculation. And this is provided by the Dijkstra algorithm, by the SPF calculation. So two things that lead to loop-free environment. So I did talk briefly about these per area databases. Now, per area databases are databases that are kept inside the area. So as I said, if we had a router that had connections to multiple areas, so let's say that this was here area 0 and this here was area 1, this router would actually have two databases. It would have the database in area 0 and would have the database in area 1 there. So these per area databases here are kept for internal and inter-area routes. That means that these databases on this router here, they are going to be carrying the information about all the internal routes in, say, area 0 here, and all internal routes for area 1 here, but also in area 1 we are going to have the inter-area routes from area 0, and in area 0 we are going to have the inter-area routes from 1. But these databases here, they need to be viewed as separate entities, because these routers here in area 0, they're all going to have the same database and share it with our ABR here on this side, but they will have no visibility in what is happening here. And the same thing would go for the routers that might exist in this area 1. All these routers would be aware of all of their links, of all of their LSAs, but they would not know anything about what is happening here except the summarized reachability information that is going to be injected by the ABR. These are going to be our type 3 LSAs, and I will talk about them in great detail. Also, the per area database here may contain NSSA external routes in a case that we are dealing with the NSSA area. So NSSA routes, they do not exist outside the per area databases. However, there is one database that is global for the entire OSPF domain with two exclusions, and these are NSSA areas and actually, I should mention here, I forgot to write it down, and also stub areas. So excluding NSSA and stub areas, external routes are global. They are kept in one single database for the entire OSPF domain. So how can we look at this information? First, warning that I'm going to give you right now, that I'm not going to be showing you this right now, because remember, the contents of the database are link state advertisements, and I still have to talk about the LSAs. So me showing you LSAs in the database right now wouldn't make much sense, but I will do that in a moment. So the command that we can run to query the information in the database is simply show IP OSPF database. If you're running multiple OSPF processes, and that is possible, each separate process will have their own set of databases, per area databases and per domain databases, and you can query those individual databases like with command show IP OSPF 1 database or show IP OSPF 2 database for OSPF process 2. And then after this database, we can specify, for example, the area ID that we want to look, the LSA identifier, the LSA type, what is the originator router, and so on and so on. So let me explain these terms a little bit. Each LSA is identified in the database with several components. These several components are primarily the link state identifier, which can be different thing depending on what is the type of LSA. It can be either the router ID of the router that injected this LSA, which is also called advertising router, which I'm going to talk about in a moment, or depending on the LSA type, can be the network being advertised. And this is going to be true in a case of type 3, type 5, and type 7 LSAs. So router ID of the advertising router would be the LSA identifier in a case of type 1, and IP network being advertised or being concerned about this LSA will be there for type 3, type 5, and type 7, and I forgot to mention for type 2 LSAs. So what is the advertising router? Advertising router is the router that injected a particular LSA. This information is going to be kept throughout the flooding scope of the LSA. And flooding scope is a very, very important concept in LSA. And flooding scope is, I'm going to read what it says here, is a distance in terms of a link, area, or domain that LSA will reach. Now, let me say that in plain English. When the LSA is injected, when it's generated by the advertising router, let's say that we have our R1 that injects some LSA into the database. This information will be communicated to other routers. So, for example, R2 and R3 in this case. But let's say that R2 here is connected to some router R4. If R2 and R4 are in the same area, R2 will have to forward this information as is to R4. But let's say that R4 here is connected to R5, which happens to be the ABR. Now, if this was an internal route here, this is where the flooding scope for type 1 LSA would end. And I'm going to talk about individual flooding scope for different LSA types. But for now, just understand that this will go up to R5, but it will not go beyond here. So for this LSA, for type 1, we can say that the flooding scope was within the area. But it also means that within this area here, this LSA cannot be modified in any way. It cannot be changed. That means that no information in this LSA can be modified, added, or removed, not even the metric, and the LSA itself cannot be filtered. So if it exists in the database here, it must exist within its flooding scope. So it cannot be filtered in any way. So the advertising router is the router that injects the LSA. And as I said, this information is kept throughout the flooding scope of the LSA. And this is going to be identified, the advertising router in the LSA will be identified not with its IP address, it will be identified with its router ID. Also, LSAs, depending on their type and depending on the information they carry, they may contain other important bits of information, like for example various flags, like the flag indicating that the router is the ABR or that it is an ASBR, or the loop prevention in, say, MPLS layer 3 VPNs that are outside the scope of what I'm saying now, but I'm just using that as an example of the information that could be additionally carried in the LSA. Also, we could have, for example, in a case of type 5 and type 7 LSAs, we could have the route tags carried there as well. We still have a thing or two to talk about the OSPF database, but I'm going to do that after we talk about different LSA types. So let's go through the list of those LSA types that we are going to be encountering in day-to-day use of OSPF. The first LSA type is type 1, also known as the router LSA. The contents, the important contents of this LSA are the router ID of the router, which is also going to be the LSA ID of type 1 LSA. And in the case of type 1, the router ID, the LSA ID carried in type 1, and the originator, the router that injected the advertising router, will be the same information. Also, additional contents of type 1 LSA are going to be all router interfaces that have been enabled for OSPF, and in some cases, depending on the interface type, we are going to have the information about the relationships on those links. Do we have any neighbors, and are we adjacent to those neighbors? And as I said, the originator of this LSA will be every single router in OSPF domain. So every router in the OSPF domain will generate their own type 1 LSA and list this important information in it. The flooding scope of type 1 LSA is going to be an area. So type 1 LSAs cannot leave individual areas. Type 2 LSA is generated by the designated router on the segment. So when we have broadcast and non-broadcast network segments, you know that they are going to elect the designated router, and this designated router is going to generate type 2 LSA representing this entire network as the pseudo-domain, we talked about this, to the rest of the network. And this representation to the rest of the network is going to be done through the services of type 2 LSA. So the contents of type 2 LSA are router IDs of all routers connected to this network segment and the net mask that is used on this network segment. And the flooding scope, just like with type 1, is going to be the area. So type 2 LSAs, type 2 information cannot leave individual areas. Now, when we have information that needs to travel between the areas, when we want to provide the reachability between different areas, this information will be carried by summary LSAs. Now, they're called summary LSAs because really what they are summarized information from type 1 and type 2 LSAs. The ABR, the border router, will calculate the cost to reach individual networks, and it's going to summarize this information and advertise into other area. By summarizing here, I don't mean perform IP summarization. That too can be done by the ABR during the same process, but by default what is being summarized is the information about type 1 and type 2 LSAs. We are hiding the complexity, we are hiding that information from other areas. So the contents are calculated routing information for area routes, not routers, but routes, based on the information from type 1 and type 2 LSA. So all I had to do was really just read what I already wrote here. These LSAs, type 3 LSAs, will be generated by all area border routers, and the flooding scope of these type 3 LSAs is going to be individual area in which it's generated. Now, when this information goes from one ABR to another ABR to another ABR, and I'm going to explain this when we talk about the inter-area operations in OSPF, which is a separate story and much more complex than I have time for now, but I will talk about it. When this is the situation, then we are going to have another type of summarization here. So we are not only going to be summarizing type 1 and type 2 LSAs, but there is also going to be summarization of type 3. So type 3 can summarize type 1, type 2, and type 3 LSAs as well. Type 4 on its own makes not much sense, but it actually works in conjunction with the external route. So I'm going to first explain type 5 LSAs. When we have any router anywhere in our OSPF network that actually redistributes external routes into the OSPF, these routes are going to be injected into the OSPF domain as type 5 LSAs. Now, these type 5 LSAs will have the information about what are the redistributed external routes, and the LSA identifier for type 5 LSA will be the actual network that is being redistributed, but we are also going to have the information about what is the originator, what is the advertising router, which will be the ASBR in our case. Now, if we take a look at this, the entire domain, except the stub and NSSA areas, is where these LSAs are going to go out. So when these LSAs are advertised throughout our network, the information about the router ID of the router that generated it is going to be carried with this route. Now, this means that when this type 5 LSA leaves the area in which it was generated, in which it is injected, other routers may not know about the router ID of the ASBR that injected this route. And in order to actually figure out how to reach this external prefix, how to reach this router that injected this external prefix, type 4 LSA will be generated by the ABRs in those areas that contain the ASBRs. And the contents of type 4 LSA will be the router ID of the ASBR from another area. And again, this is something that I will explain in a little bit more detail when I talk about external routes and inter-area operations. Last but not the least, there is type 7 LSA. Type 7 LSA is specific for not so stubby the NSSA areas, which do not, generally speaking, support external routes. They do not allow type 5 routes, even though the flooding scope is entire domain, see here, not in the NSSA areas. So they do not allow type 5 routes to enter the NSSA area, but they can inject themselves external routes into the rest of the OSPF domain. That means that there can be an ASBR in the NSSA area, but because NSSA area does not support type 5 routes, these routes will be injected as type 7 routes. So when they are sent throughout the network with the flooding scope of an area, one of the ABRs that sits between the NSSA area and the rest of the network will actually translate this type 7 into type 5 LSA. And again, I will talk about this when I talk about the inter-area operations in OSPF. Does this make this information here incorrect, that type 5 is generated by ASBR, because I just told you that it can be generated by the ABR as well? Not so fast, because that router that actually translates type 7 to type 5 is technically speaking going to become an ASBR, but logically speaking we might be perceiving it as an ABR. This will become a little bit clearer in a short while. So these are the LSAs that you are most likely to encounter in your network. But there are some others. These are type 6, type 9, type 10, and type 11. There is also type 8, but that one is not used in OSPF version 2. It is used in OSPF version 3 for IPv6 routing. So type 6, also known as group membership, and also called multicast OSPF by iOS, is not supported by iOS, but it can be gracefully ignored. Now, what do I mean by it can be gracefully ignored? OSPF is designed in such a way that when routers receive an LSA within LSA type that they don't understand, that they don't support, the routers are supposed to tear down the adjacency with the neighbor that sent them this malformed LSA. So if we receive type 6 LSA that iOS doesn't support from, let's say, equipment that does support type 6, some other vendor, we are going to tear down the adjacency. That's not a good thing to do. So iOS does allow us to gracefully ignore type 6 LSAs. And this is the only thing you can do about type 6 LSAs in iOS. Type 9, type 10, and type 11 are so-called opaque LSAs, and they're different because of their different flooding scopes. The flooding scope of type 9 is a single link, and this is not widely used in OSPF version 2. It is used by extensions provided by the NSF infrastructure, or the non-stop forwarding infrastructure, to communicate between routers that actually support these NSF extensions. Type 10, on the other hand, is relatively widely used in service provider networks that utilize MPLS application called the traffic engineering, which can use something that is called the constrained shortest path first calculation, where we are not only taking into account the link cost like with normal OSPF, but we are also taking into account some of the link attributes, like for example the affinity bits, also called color of the link, and the actual bandwidth. So not the calculated cost based on the bandwidth, but the actual bandwidth available on that particular link for a certain application that can be used. So this is information that can be used, or this LSA is used to communicate these advanced link attributes throughout the OSPF network. And there is also type 11, which is a domain local, or I should say domain wide or domain global opaque LSA, but I am personally not aware of any OSPF implementation of the domain wide opaque LSAs. I promised, and I'm a man who keeps his promises. The time has now come for OSPF database part 2. In this section, we are actually going to take a look at the database of running OSPF configuration. If you remember, we already have some OSPF configured. We have our router R1 connected to our router R2, and remember, on R1 we have that one loopback interface. So here we have interface gigabit 1, interface gigabit 1, and this is 192.168.12.0/24, and here we have 192.168.01/32. The OSPF is already running here, which means that R1 and R2 do have their databases. So let's take a look at these databases. We are going to start with R1. The first command that I'm going to run is going to be show IP OSPF database summary. Now, what this information here is going to show me is some summarized information about the database. So here I have the information, like for example, that we are running OSPF with a router that has the router ID of 0001 in the process number 1. And here I have the information about area 0 database summary, and I have here information about the router LSAs. I can see that I have 2 router LSAs. That's type 1. I see that I have no network LSAs, no type 2s, no type 3s, no type 4, no type 7 here, and I can see here that I don't have any opaque LSAs for either the link or the area. Also here I can see in the process 1 database summary. Now remember, this one here, this was the information about the area 0 database. And remember what I told you, we do have per area database, and we also have per process or per domain database. And the thing that was missing here, if you paid attention, from this output was any information about type 5 LSAs, because type 5 LSAs are technically speaking not part of any area. So here we have the information about type 5 LSAs, and we see that we really have 0 of these LSAs. Another information that we are going to see here is the grand totals. I can see that I have a grand total of 2 LSAs, and this non-self means that I have one LSA that is not generated by the local router. And given that I have only 2 routers in my network, and I'm looking at the information on R1 here, it's logical to expect that I do have one non-local information in my database. So this is the first command that I wanted to show you. A quick overview of the database summary. The second command I'm going to show you is going to be show IP OSPF database. This is the summarized database information. Now, if you might remember, when the OSPF routers are forming an adjacency, at one point they're going to be database descriptors exchanged. And this is pretty much that information. So this is a quick overview of the OSPF database. And here I can see what are the link IDs of my LSAs, and I can see here that these are the router link states, and this indicates type 1 LSAs in area 0. So I can see that I have 2 link states, one with a link ID of 1 and the other one with a link ID of 2. And you might remember that the LSA ID of the type 1 LSA will always be the same as the advertising router of that LSA. And I can see here that I have the LSA 0001 that has been advertised by 0001, which is R1, and I have 2 that has been advertised by 2. The age is simply the information how long ago, in seconds, this router learned about this information. The sequence number here is simply the serial number, so to speak, of this LSA, and the checksum is some basically cryptographic checksum over that information, just to make sure that the information is actually correct in the database. And finally, at the end here, we have the link count. How many links are described in this LSA? And here we have information that 3 links are described. And here in this LSA we have information that 2 links have been described. Now, again, if you paid attention to what we are doing, you're going to be scratching your head a little bit now. R1 has 3 links and R2 has 2 links. If we take a look at this output here, we can see that R1 clearly has 2 links and R2 has 1 link. Well, this makes no sense, so let's take a look into the database and see what this is all about. So what am I looking for? I'm looking for the OSPF database, and what I want to do now is I want to take a look at type 1 LSAs. So this is going to be the router keyword here because it's going to show me the router link states. And remember, router link state is type 1 LSA. So this is what I want to be looking at. So I'm going to say router. But what am I looking for? I can either enter the link state ID of the LSA, in which case, let's say that I want to take a look at the one learned from R2, I would enter this command, or I can say that I want to see this information advertised by R2. And in the case of type 1 LSA, the advertising router and the link state ID will always be the same value. So this is going to yield the exact same thing. Or I can, for example, take a look at the self-originated LSAs. And then this would show me the same information as, for example, this command would show me. But let's take a look at what is the LSA that R2 injected. So this is the information that I'm going to have in my database. Now, this is going to be separated into two logical parts. So I'm going to divide them like this. This first part here is the LSA header. This information is going to have information about certain options. Remember that other data that I mentioned before. It's going to have an indicator what is the link state type we are talking about, and router links indicates that this is a type 1 LSA. We are going to have information about what is the link state ID and what is the advertising router. We are going to have the information about the sequence number, the checksum, and how long is this information here in bytes. And I'm going to have the information about how many links are described by this LSA. Now, this bottom part here, this part here are link entries, and I see here that I'm expecting to see 2 link entries, and I do have 2 link entries described here. Now, let's go back to here and see, as I mentioned before, I do have a single link. So how can it be that I'm seeing 2 links in the database? Well, remember what is the content of type 1 LSA. The first information is about the router links, and the second is about relationships. In other words, the neighbors. So how many neighbors on this link does R2 have? Well, it does have 1 neighbor. R1 is the neighbor of R2 on this link. So if we were to describe the neighborship as kind of a link there, I will end up having information 2. Now, or 2 link entries. Now let's take a look at R1. R1 says, if you remember, that it has 3 links. Well, one is obvious, another one is obvious, and if we describe this relationship here as a link as well, we are going to end up with the number 3, which is going to be exactly what we are expecting to see. So going back to the terminal here, I can see, and I'm going to start from the bottom here, that this part here actually describes the link. I can see here that it says it's connected to a stub network. Now, stub network in the database here simply means that this is not connected to any routers. Now, this is not true, we know that, but this is how this is going to be described. When we have a point-to-point network type, this is how it will be described in the database. And we can see here that the network is 192.168.12.0 and that the network mask is 255.255.255.0, and we can see that the metric is 10. All correct information and what we expected to see. Now, this link entry here describes, from R2's perspective, the relationship between R1 and R2. If we take a look at it, it says here that link is connected to another router. It says it's a point-to-point relationship. And we have the information about what is the neighbor's router ID, and we know that the neighbor's router ID is 0001, and the router's interface address, this is our local router's interface address here, is 192.168.12.2, which basically helps the router associate this information with this stub network entry, because based on this subnet and mask, we know that this relationship must be on this particular interface here. Very neat. We also have information about the metric, but this really is not relevant. This metric information here will be used to calculate the costs. So this is the information in the database on R1, but I'm looking at R2 here, am I not? Well, that's the beauty of OSPF. When R1 and R2 are in the same area, it doesn't matter on which one of them I look at the database. This database will be identical on both routers. Let me show you. So I'm going to say show IP OSPF database self-originate. This is the information from R2. Oh, sorry. Database router self-originate. So here, I'm now going to switch quickly between my 2 tabs. So now more R1, R2, R1, R2, R1, R2. And you can see that the only thing that seems to be changing is the LS age, which again makes sense, because if R2 injected this information, it stands to reason that this is a little bit older than the information on R1. But everything else you can see now, I'm still switching between them, that all the information is exactly the same. So this is the beauty of OSPF, that it doesn't matter on which of the routers you're looking into the database, you're always going to see the exact same information. Now, let's take a look at what R1 says about this relationship. So if I say show IP OSPF database router self-originate on R1, I'm going to have pretty much same information as before, but remember, R1 has one extra link, and that extra link is very simple to find. Here it is. this is how the loopback interface will be described. It's described as a stub network. We have our network and the mask, and remember, regardless of what mask we configured, by default we are always going to get /32 in the database of OSPF, and we can see that it has metric 2. Now, these two link entries here describe the link itself and the neighborship relationship with R2 here, just the same way as it was described on R2. The only difference really is the router interface address, which in case of R1 would be obviously R1's address. Let's expand our example a little bit. So what we have so far is we have R1 and R2. Let's add R3 and R4 to the mix. And R3 and R4 are going to be on a shared segment with R1. So what I'm going to have here is 192.168.1.3.4.0, and it's going to be /24, and this is going to be gigabit interface 2, and gigabit interface 2. And this is all going to be in a single area, so I'm not yet going to be looking at any additional areas. Not yet. I will introduce other areas later on, but for now, this will do. So what I'm going to do here is I'm going to enable this relationship here, and I'm going to configure one additional thing. Let's say that I want to make sure that my R3 here is the designated router, and I want to make sure that R4 and R1 are ineligible to become the DR. So this is a configuration that I'm going to set up now. How can I make sure that R3 is the DR? I'm going to make sure that it has, first of all, non-zero priority, and that it has priority higher than R1 and R4. But how can I make sure that R1 and R4 are never going to become the DR and BDR? So I'm going to set their priority to 0, which then doesn't matter which priority I use on R3, because even the default priority of 1 will be more than enough. But just for fun, I'm going to set the priority here to be the maximum value, 255. So I'm going to bring this into the mix, and then we are going to see how this network here will be represented, how the adjacencies are going to be on this network here, and then we are also going to observe how R2 perceives this relationship here. As always, the first thing that I'm going to do is I'm going to make sure that my layer 2 is okay. The first thing I'm going to do is on R1, I'm going to say show IP route connected, and what I'm looking for here is this route 192.168.1.30.4.0, and I want to make sure that it's connected on gigabit 2. And then I'm going to test whether I actually do have reachability between my routers 1, 3, and 4, and from R1 I seem to have it. On R3, if I do show IP route connected, I'm going to see that I do have this route in place there, so I'm just going to say ping 192.168.1.30.4.1, I can ping 1, and I can ping 4. On R4, show IP route connected, I have the route, I can ping 1, and I can ping 3, which means that my layer 2 is operational. Let's now configure the rest of this setup. So reminder, I want to enable OSPF here, and I want to make sure that R3 is the designated router, which means it's a very good place to start by configuring R3. But before I do that, I seem to vaguely remember that